First of all, thank you, Midas and Xiaofan, for allowing me to do this presentation. This was a analysis that we did a few years ago, and with using one of the Midas suites of software. A little bit about me. I'm originally from Peru. Um, I've been living in the Tampa Bay area in Florida since 1990. Um, I did my bachelor's at the Pontificia Universidad Católica del Perú, and I did my master's in the University of South Florida. I've been with ACOM for over 21 years, and as Xiaofan mentioned, I specialize on long span bridges, computer analysis, structural design, and so on. This is going to be the agenda for today. I would like to thank Andrew Smith with Wisconsin DOT and my colleague Bob Anderson. What we're going to be looking at is we're going to do a little bit of preliminary theoretical background on the redundancy. What's redundancy? How do you define it? What's the importance of redundancy? And then we're going to be looking at this project that we worked on for Wisconsin DOT for evaluating the redundancy of, it was a couple of um, steel box girders. Before we did when we first obtained the program MIDAS FEA, we did numerous test evaluations just to make sure to convince ourselves that the program was working correctly and that we were doing what we were expecting of the software. So what is redundancy? This is from the AASHTO manual for bridge evaluation. It's basically the capacity of a bridge to carry loads after the bridge is damaged, or maybe one of its members fails. So that's what redundancy is. So if one of the members of the bridge breaks, ruptures, can the bridge still hold load, at least for a certain number of, or for a time until it's closed and repaired? What type of redundancy do we know of? We know of structural redundancy. We know the load path redundancy and internal member redundancy. Now, all these definitions are widely known. They're from AASHTO and from other references. Structural redundancy is basically a indeterminate structure, allows for the load to be redistributed to other load paths. For example, let's put a very simple example. If we have simply supported beam pin on one end and rolled on the other one, if the beam breaks in the middle, the beam falls. But if we have a beam that, for example, has 3 spans and the middle span breaks, you still have capacity of the beam because the beam gets supported by the by the middle supports. So that's a simple way of explaining structural redundancy. Load path redundancy. This is, for example, if we have a bridge that has 9 girders, 9 eye girders. If one of the girders breaks somewhere in the middle, we have 8 other ones that can share the load of the ruptured girder. So that's what load path redundancy is. And internal redundancy, this is a little bit more intricate, and it has to do with, it's basically this, almost similar to the previous one. At the end, redundancy means that if one of the major important elements of a structure breaks, the load can be redistributed via different ways to the other members. That's redundancy in a nutshell. And how do we define redundancy? This is a graph that shows there's two graphs. There's what's called a pristine model, which is the top one, and we can load the structure. This is a load versus capacity. We can load the structure beyond the capacity of 1, and we still get our response. As we load the bridge more and more and more, the structure starts to deform more until it breaks. In this case, this graph shows that this pristine model, and this is just a sample graph, it doesn't represent any particular bridge or structure. This particular structure ruptured a little bit over 3 times the, actually on the left side, the vertical axis is total number of live loads. So we add the dead load, which is the little bottom part, and then we add number of live loads. So this one ruptured at about a little bit over 3 times the the uh, live load. The second one is called the damage model, and again, this just represents what is the how do you measure the capacity of a structure. And in this case, um, the model or once it's damaged, uh, the deflection grows a little bit faster than in the pristine model, and it could only hold a little bit over 1 time the live load. This is just a graph that shows um, how to measure the capacity of a structure. So when we look at redundancy, we have these two parameters, the LF1 and the LFD. And what that does, what that tells us is what is the reserve capacity of the structure to resist live load. It's kind of it's basically like a low rating factor. So we got on one side we got the nominal capacity, on the other side we got the dead loads, and at the bottom we have the live load. So this gave us the reserve capacity. We got two parameters. One is for the pristine structure and one is for the damaged structure. So once we obtain those parameters, in order to determine the redundancy capacity of a structure, we use those numbers to calculate another factor that we're going to see in the next slide. This one shows that the damaged structure also has a dynamic effect. When a beam breaks or when something breaks or snaps, there's a dynamic effect. So we're going to add that dynamic effect to the dead loads before finding the damage structure factor. So once we get the pristine structure factor and the damage structure factor, LFD and LF1, when we divide those, if we obtain a number greater than 0.5, we can say that the structure is redundant. That's a definition of redundancy. So why do we care if a structure is redundant or not? Why is it important? AASHTO defines a system to be redundant, and I'm just going to read it. It's a steel primary member or portion thereof subject to tension for which the redundancy is not known by engineering judgment, but which is demonstrated to have redundancy through a refined analysis. So those are just some words put together that tells me that I have to do a refined analysis to find out if a member is part of a redundant system. Again, why is redundancy important? So basically, we're gonna, when we design a steel bridge, we have to identify which members are fracture critical members, because they're special members and they have to be, they have some special considerations. So a fracture critical member is a member, is a steel primary member or portion thereof subject to tension whose failure would probably cause a portion of the entire bridge to collapse. So why do we, again, what is redundancy? How does this, why is it important? and what does it have to do with fracture critical member. So we see here that a tension member, when it breaks, um, the failure will cause the collapse of the bridge. So fracture critical member is very important. Again, why is redundancy important? So uh, a fracture critical member has some special design considerations. It has some special fabrication considerations, and it also has some special maintenance considerations. And when we were asked to evaluate the redundancy of two twin box flyovers in Wisconsin, um, we needed to demonstrate that the bridges were redundant because of the inspection part. The bridges had been designed as fracture critical members, so they had all the the corresponding load factors and the corresponding um, welding procedures and the specialty steels used for fracture critical members. But if we were to demonstrate that the bridges were redundant, the maintenance part could be reduced, so they can be maintained as non-fracture critical. So in order to accomplish this, we looked for several possibilities to use different softwares, and most structural softwares are very good in the regular bridge analysis or structural analysis, but very few are made for detailed analysis. And we considered a few, and we ended up choosing MIDAS FEA for this project. MIDAS FEA is one of the several software of the MIDAS suite. So why did we choose MIDAS FEA? Number one benefit that I saw in it was the ease in modeling, and I'll talk a little bit about that. You can't really go through everything in the few minutes of a presentation, but it is very easy to model in MIDAS FEA. You also have construction station analysis, which is important because the stresses need to be put into the structure at the right moment. For example, when the wet concrete is put when the steel is not composite, and then some other loads are input when the structure is composite. So you have to have construction station analysis. The program has all sorts of elements: beam elements, plate elements, solid elements. It has a special interface element which we used for the shear studs. It's an interesting element that can have a length 0. You can have two nodes in the same space and define that element with a local axis and some stiffnesses. The program has material nonlinearity. It has geometric nonlinearity. It has something called concrete total strain crack model, which models a concrete in compression and in tension when it cracks, and it becomes it basically disappears from the model. They also have reinforcement embedded in concrete elements, which was also important because during the redundancy analysis, we have to use every part of the bridge to help with the load path. And finally, has different ways of analyzing convergences when you are using material nonlinearity. You can see some of the ones that are available. So once we got the software, before we did anything with the project, we spent some considerable amount of time doing tests and verifications. We always, as engineers, want to make sure that the program is doing what we think it should be doing. So we did a cantilever beam made of plates. It was a reinforced cantilever beam, and we compared it against theoretical results or using a program such as Response. We did a fix beam. This was to make sure that boundary conditions were taken care. Also, this was a reinforced concrete beam made out of plates. We did a two-dimensional flat plate. Again, this was also a a flat plate that was reinforced. It was a square plate and it was fixed along the edges. And finally, we did a test that was really critical, and it was the results that we got, and you'll see them in a little bit, were really amazing. University of Texas at Austin did a small bridge that it was a small scale bridge, and it was tested. It was failed. The bottom flange was and webs were fractured, and then it was loaded until failure. So I'm going to talk a little bit about this for a few minutes because it was very interesting. This was a full-scale bridge. It was a 120-foot span. It had a little radius of curvature. You can see the size of the boxes were 4'9", and they were spaced at 12 feet. The deck was 23 foot 8 inches wide, and it was an 8-inch deep reinforced concrete deck. This is a view of plan view of a section cut of the sample bridge. This is an actual picture from J.B. Newman thesis from University of Austin, Austin, sorry. And this is how it was loaded and the failure of the deck. So we modeled the bridge exactly as it was in this small project. And this is the view of the bottom flange and the web fractured with a load on the top, similar to the one that we just saw on the previous slide. And this is the picture of the real deal. You know, you see the bottom flange and the web fracture. This is a plot. On the left side, we got the results from MIDAS FEA. We did two models because in Texas, the barriers are not continuous. They have gaps, but we did one with gap and one without gap. And you can see that somewhere around 300 kips, maybe around 300 kips, the bridge starts to fail. It deforms more without accepting more load. And then on the right side, you see the actual results from the physical test, and the capacity was about 350 kips. So we got pretty good correlation between the MIDAS FEA results and the physical test. So with that, we were happy with MIDAS FEA. So how do what methodology did we use to determine redundancy? So number one is we created a nonlinear advanced structural model, and the model uses the best estimate for material response. And I'll talk a little bit about the material properties we used in a little bit. We used a set of two HL93 loads that we multiplied by a factor, and we positioned laterally in the worst possible location for the critical point that we were looking at. So we identify which location of the bridge had the highest possibility of fracturing, which is typically in the location of the maximum positive moment and at the end spans. And then we analyzed the internal state due to dead and live loads, multiplied it by a dynamic factor, and then we increased the live load until failure. These are some of just the characteristics of the actual bridges. This is a interchange State Road Highway 29 with US Highway 41. We had two units. Each unit, the first unit had 4 span. The second unit had 6 spans. This is the cross section of the first one of the first bridges that we looked at. We looked at 2 of the several bridges. This is the other unit that we, or the other flyover that we looked at. This one had three units with 15 span totals. You can see on the right column the length of the spans. This is the cross section. It was a little bit wider, but it was basically very similar to the previous one. Um, for the redundancy analysis, originally we had thought of using brick elements for the deck, but since you have to divide them um, in the thickness of the deck in maybe 1 inch increments, and then you got to divide it longitudinally, it proved to be very, it was going to be a very big size model, and the runtime was going to be tremendously high. Eventually, we decided to use um, plate elements. We did some tests to make sure that the plate elements, number one, that it could um, have reinforcement elements attached to them, which it could, and that the total concrete strain model would could be used, and which it could. Another thing that we had to take care was the shear stats. The shear stats are a very important part of the equation in redundancy, because as the girder breaks, it pulls down the deck, and as it pulls down the deck, the load goes from the girder to the shear sets to the deck, and from the deck goes to the other girders or to the other elements that are helping with the redundancy. So we had to make sure that those shear set elements had not only pull-out capacity, but some sort of shear capacity. And then also we had to find out when something breaks, we all know that there's a dynamic effect. So it's not only the load that is in the beam that gets transferred to the other part of the structure, but there's a dynamic effect too. So these are some of the material properties that we used in the analysis. This is the steel box girders were linear elastic with some soft hardening, basically very vertical curve, and then a very flat plastic hardening. This is the compression and the tension for the concrete. We use a Thorenfeld model. You can see the relationship between the stress and the strain on the top. We had a little bit of tension hardening, so it does take a tiny little bit of tension, but then it basically ruptures. This is the material properties of the reinforcement. It's a 60 KSI yield steel, but it does have a better strain hardening. Goes up to 90 at rupture, 90 KSI. For the steel boxes and the diaphragms, we use 4-node shell elements. For the bracing members, we used 2D truss elements, anything internal. One of the interesting things was that we wanted to model the bracing members not only that have a tension failure. In this case, it was linear elastic, so it goes up to 50 KSI, and then it basically holds no load. But we also wanted to have them fail in compression under buckling, so we used the same total strain crack model that we use for the concrete for the compression of the bracing members. So it got to a certain load, and then it just basically buckled, and it didn't provide any more resistance. The deck elements, like I said, we decided to use shell elements just to not make these models big and clunky to use, because we spent a lot of time running many models, many alternatives, many increase in loads, and there was a lot of time spent waiting for the models to run. We did use solid elements for the parapets, for the barriers, and that is also a very important load path. In the Texas model, in the University of Texas at Austin model, we saw that in both in the pictures and in the FEA results that the loads went from the deck to the barriers and then back to the deck further from the fracture and then back to the other girder. So the parapets were important in this analysis. And then we used, these are the interface elements that we use for the shear stat. Again, you can have the two nodes at a distance, or you can have them in the same point in space with a zero length. And then you can give it different stiffnesses in the different orthogonal directions. So this is one of the bridges that we analyzed. This is unit 2, span 5. It was the longest, it had the longest end span. And we chose the outside girder right at the point of maximum positive moment. It's, you can see down at the left bottom corner of the slide. So I'm going to start showing some of the MIDAS FEA. The reason why I think MIDAS FEA is it's easy to model is because MIDAS FEA, in a regular program, structural program, you have to create your coordinates, whether you use them, you do them in the program or in the spreadsheet. You got to create your nodes first, your coordinates of your nodes. Then you got to create your elements, your connectivity between node and node. And again, you can do it in the program itself. If you have a small model, you know, it's fairly simple, or you can use a spreadsheet, or some programs now have a lot of different ways that you can create them graphically, or well, in MIDAS FEA, you first create geometric figures. You can have lines, you can have planes, you can have solids, and they're just geometry. A solid could be a box that has a width, a depth, and a length. It's just a geometry box. In this case, and I'll show this a little bit further in. In this case, this is a view with my geometric lines and the model itself. But in the next slide, I take out all the model elements out, and I just leave the geometric. All these are lines, um, and they're just geometric lines. You know, you got a starting point and an end point, and all those lines are plates and solids that you can create in MIDAS FEA. You mesh them, and they're meshed automatically. You don't have to node what you don't have to know the node numbering, or you don't have to worry about the node numbering, the element numbering. Everything's taken care of for you. So in this case, there's, I don't know if you can see them, but you see a mesh of blue lines at the top going transversely and longitudinal. Those are all the reinforcement. And again, those are lines. First, everything is a line element, is a geometric line, and then it gets converted into a finite element member. This is a view from afar of the bridge. You can see the curvature of the bridge. I'm going to zoom in a little bit. You can see the parapets are solid elements. The deck is our shell elements. You can see the end diaphragms, they're shell elements. And you can see the shear studs. They're like little white stars on top of the webs. The webs are the kind of brick colored plates. This is a view, the same view, but now you have the reinforcement elements, the steel reinforcement elements. There's transverse reinforcement and there's longitudinal reinforcement, just as in the real bridge. This is a view of the reinforcement only. The reinforcements are embedded in the concrete, so when the concrete deforms, the rebar also deforms. They're 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 uh, they're joined together basically, and it's all joined by the program. You just tell this reinforcement goes into this concrete, and then the program does all the background work. This is a view of the two steel boxes with the internal frame, and this is again just showing the curvature of the bridge. And this is a little bit of a zoomed in without the deck. You can see the diaphragms, end diaphragms, intermediate diaphragms. You can see the top lateral bracing, and you can see the anterior cross bracing. This is a close-up view of the parapet and how it's connected. It's connected rigidly to the deck elements, the deck plate elements. Now, this is a side view of how we created the fracture. We had about, I'm going to say 20, I haven't counted them, but maybe 20 nodes along the both webs and the bottom flange. And when you have that amount of nodes and you only have 2 nodes at the other ends, you gotta mesh it correctly so that all the plates are connected. This is a side view. This is a view from the bottom. You can see the bottom flange is also meshed up. And what we did was, in order to mimic a progressive failure, we started unbuttoning the bottom flange node at the middle. And what we did was, there was basically 2 nodes in the same space. One node belonged to the left side of the girder, and the other node belonged to the right side of the girder, and they were connected with a infinitely rigid spring. So we started by removing the spring at the middle, and we worked our way out towards the webs from either side. When we got to the webs, we removed the springs from the webs one by one until we got to the top. So it was a progressive failure. It wasn't a one-step failure. This is another view of the shown from inside of the uh, of the failure plane. Here's another view, just showing the meshing. Now, this is why it's important to have construction stage analysis in your program, because this shows not only putting the loads in the right time and at the right compositeness of the structure, but also in order to create a fracture. And this is what I said, we create a fracture by removing one spring at a time. So you got 26 steps in which we removed each of the springs to create the progressive failure. So this is the truck load that we put. We put the truck load and the lane load, the ASHA typical HL93. We put them in the location that would produce the maximum moment on that outside girder. So it's placed all the way to the edge of the barrier. This is a view of the 2 trucks placed towards the edge of the barrier, just as in the previous screenshot. And this is a view of the lane load. Again, this is pushed all the way to the right barrier. So those are the live loads. So I'm going to show some plots of the program has really very good graphing capabilities to see the formation, stresses, forces, basically any of the results that you would like to see. So this is a plot of the displacement. You can see the blue part with the highest displacement is about 32.5 inches. You can see the girder opening, that's the fracture. This is another view, a little bit closer. You can see both the bottom flange and both webs fractured, opened. You can see a little bit of delamination between the top flange and the deck. The studs did have capacities, pull-out capacity. So when it reached the pull-out capacity, they broke off basically. So as you move along at either side of the fracture, eventually the studs picked up again. This is a view of the stresses when you fracture this. When you fracture the right girder, you can see the little gap in the fracture. The left girder stresses go up because it's basically now taking the load that the right girder used to take. The bottom flange stresses in this plot show red is about 56 KSI. So you can see here some of the distribution of forces, that structural redundancy we were talking about earlier. This is a view of a little bit further in. The stress is kind of normalized as we go to the other spans. This also shows there's so the fracture happened at the midspan. So that means that since the right side fracture, the left girder had a big positive bending moment. So the bottom flange goes up to 56 KSI in stresses, but also at the pier, the bottom the um, the bottom flange also has bigger compression stresses because now again the left girder is taking most of the load. This is a plot of the deck. When you do shell elements, you can plot the top stresses and the bottom stresses. This is the top stresses. So what we can see, some things here we can see is that the maximum stress in the concrete is about 280 psi, which is the rupture of concrete. On the right side, we see high compressive stresses because the concrete is taking that side. The concrete is taking more load because there's no girder underneath, so it's trying to compress more. This is a view of the bottom fiber stresses of the deck. It's kind of opposite than before. The bottom stresses now on the left side of the girder, there's more compression than on the right side because now the left girder is taking more load, so it's the positive moment is bigger, so the bottom flange has the bottom fiber has more compression. This is a view of what they call the crack status. You can see there's a legend at the top what the cracks are. Some of them are partially open, some are fully open, some are closed, and some are not cracked. You can see that there's basically cracking in the area where the failure of the girder happened, right at the towards the middle of that span. This is another plot. This is the bottom fiber. The other one was the top fiber. In this case, we can see that the left side of the deck didn't crack, but the right side of the deck had uh, ample cracking. So this is a view of the stresses in the reinforcement. You can see that there's a limit on about 62 KSI on the reinforcement. And again, the left side of the bridge is now basically holding the right side as well. So the stresses on those reinforcements went up. This is the transverse reinforcement. Um, this is the bottom reinforcement. We separated the reinforcement in the upper, bottom, or upper layer, bottom layer, transverse, and longitudinal. This is a plot of the stresses of the parapets, the concrete parapets. You can see that on the right parapet, there's some tension because again, the right girder has broken, so the parapet is basically dropping. And then the left parapet, there's some bigger compression because it's bending more in positive bending. This is a view of the parapets close to the fracture point. Again, there's some tension in the parapets at the bottom on the right parapet. This is a view of the plots of the top lateral bracing. The top lateral bracing as well as the internal frames were modeled to have a plastic tension failure, but they were also modeled, like I explained earlier, to have a compressive buckling failure. In this case, you can see that there are some lines around the area of the fracture that don't have any values. They're basically just black lines. That means that those ones failed in compression or in tension, and they were not available to resist any more force. This is a view of those same top lateral bracing. Now, since we model them as, in quotations, concrete elements, so that we were able to see the compression failure, we can also see that they're, again, in quotations, crack. So all those that have a PL means that they basically went into plastic mode. So what we were trying to get here was a redundancy factor, right? We remember that if it's more than 0.5, um, the structure is deemed redundant. So this is some of the conclusions that we got. On the right side, you see the girder deflection versus the reserve ratio, and as we increased the reserve ratio, which means higher live load, uh, the girder deflection grew higher and higher. And this is basically at zero point 0.7. For this one, we said that we were going to deem that to be the structure failed. So we were getting results around 0.7, 0.75 for these two bridges that we analyzed. So on the left table, you can see as we increased the RD factor, how the stresses in the different parts of the structure um, behaved. So that is the end of my presentation. Xiaofeng, I'll go back to you. Thank you very much for listening. So I see some questions here. So this study was done actually about 10 years ago. And it took, I would say, a little less than a year to complete. Um, we did a lot of study of the software beforehand, and then, like I said, there were a lot of runs to be made. Can I comment about the use of shell versus plates? What were solids used for the parapets? Could plates and shells have given similar output? Deck plates in the same plane as top flanges or center of the deck. So the difference between, depending on the definition of the software, because this is very software, uh, plates are stiffer, shells are membranes. So to use for concrete, I use plate elements. And like I said, this is very software dependent. Some software calls shells plates and some plates shells. So the thing is that this is when I call this shell elements, they're plate elements in a sense. They have bending stiffness. They don't have they have an axial stiffness, but they don't. It's not a membrane, and that is what maybe you're thinking about when you made this question. That some programs call shell elements membranes. So this is a deck element. It's a concrete element, so it has stiffness in both directions, bending stiffness in both directions. Um, why did we use solids for the parapets? Because we needed to have more or less the shape, and we could have used a set of plate elements, but um, we wanted to have the right cross section, and we could do that with shell elements. Could plate shell have given similar output? Yes. Like I said, this is software dependent. The nomenclature sometimes go back and forth. Deck plates were set at the center of gravity of the deck, and they were connected with rigid links. Actually, they were connected with the shear studs to the top flanges, and they were connected with rigid links to the parapets. Welding, we did not um, have any welding. We did not model any weldings. That is more of a detailed analysis, let's say. Um, this was a full nonlinear analysis. Yes. Material nonlinearity, because the concrete is nonlinear, the steel is nonlinear. What interface elements used to model the failure zone? So incremental failure capture. I did explain a little bit. The failure zone, um, we had nodes on the same space, so with the same coordinates, but one belonged to the plate to the left and one belonged to the plate to the right. And those nodes were connected with rigid links. And in order to model the failure, we would unbutton each rigid link one by one, but in a symmetrical pattern, starting with the bottom flange middle node, and then going towards the webs. One by one, we would unbutton the spring elements, and as the spring elements were unbuttoned, the forces on the spring elements were introduced back to the structure. I think those are okay, there's two more. What was the computational time for your model? I don't remember. I'm sorry, this happened a little while ago. I haven't run those models in a while, but it was, I'm gonna say it was hours. Um, how did we choose the mesh side? Choosing mesh side is basically a trial and error. Typically, the smaller you go, the better results, obviously. But the smaller you go, the more time it takes. There's more elements. There's more output. So it's a balance. And I know back in structural analysis, we were taught a little curve that it goes up with number of elements, and then it flattens, and then it doesn't matter how many elements you add, your results don't change. So sometimes you got to do a little bit of a trial and error, and usually, typically, I'll try to go small in the elements. That way, I don't have to rerun it again. Recommended mesh size, like I said, it's a trial and error. Basically, when you mesh it more and more, and if the results don't change, that's where your mesh size should be. Can you explain the last slide, 0.5? The last slide is I'm going to show again my PowerPoint. So this is just a summary of our findings. So RD is the ratio between the pristine structure and the kind of a low rating factor versus the fracture structure low rating factor. What we did in this analysis, we actually, each model, we analyzed it with a different RD. We went from a small RD, we would increase the live load, the number of live loads that were, so we had the live load, right? We had the two trucks and the lane load. And then we used a factor for that live load. We started with a small number, and then we would go up until there was a stress in the girders that was higher than yield, and that's when we deemed it. We deemed the structure failed. So we did a lot of different runs, and that's why I said you have to have a model that makes sense, because if not, I mean, this is very time consuming. Um, so the 0.7 is just that one of the structures was quantified as 0.7 of redundancy, and the other one was deemed 0.75. Those are the I don't want to go through all the slides, but yeah, I guess I'll go through the slides just to show the formula again. So this is that RD. It's the capacity of the the damaged structure versus the pristine structure. So if this number is greater than 0.7, then 0.5, then this is deemed to be, and this is according to the NCHRP 406 report, it's deemed to be redundant. I think those are the questions. And I hope that I have answered them to your satisfaction.
Yes, thank you so much, Daniel. And thank you so much for all attendees. Thanks for your time. And do you want to provide like a brief conclusion for all the attendees, Daniel?
Yeah, I just want to say that this analysis was done for this specific two bridges. It was tasked by Wisconsin DOT. This was there was a previous to our analysis. There were some other analysis done by other consultants, and after an analysis, Wisconsin DOT had, I think it was Purdue University, do a more global redundancy study. Again, this was just for those two bridges. So there was more done after this study was done back in 2009, I believe it was, or 2010. And again, the bottom line of this was to um, when you have a non-redundant structure, you have to inspect them, and they're very onerous, they're very costly. You have to cut traffic. You have to hire inspectors, and it's a very costly, and you got to do a certain amount of time. If your structure is deemed redundant, you don't have to inspect them as often. So it's a cost issue, basically. Cost
Okay,
versus
thank you.
safety, of course.
Mhm. Thank you so much. Thank you so much, Daniel. Just want to tell everyone, the session will be recorded, and we will send out the review page follow-up email with the recording video and also the presentation file. And we'll also have a quick survey after the webinar. It will pop up once you close the webinar. Please take 30 seconds to fill in for us, and we really appreciate your help. If you receive the confirmation email of discussion session, please join the session at 4 p.m. with link attached. And Daniel is one of our MIDAS expert influencer from Microsoft Expert Network. It is a networking platform for engineers to learn from experts' experience and also insights. We have more than 60 expert engineers. If you have any technical problems with your project or in general, you can always let us know and join like a QA session with our expert influencers to learn by discussing with experts and also other experienced engineers, or let us know like your situation. We can try to connect you to our expert influencers based on your needs. One thing I always believe is that when a group of smart engineers come together with different perspectives, you can always receive fresh ideas. Exchanging information on different challenges in the project, experiences and goals will all allow you gain like new insights. Thank you again. I really appreciate everyone's time today, and have a good day, everyone. Thanks so much, Daniel.
Thank you.
Thank you.